Welcome to the third lecture on module 3 on mass transfer operation. In this module, we are discussing equipment for gas liquid operations. So, before going to the next lecture, let us have recap on our previous lecture. In our previous lecture, we have mostly considered the tray column and its different internals. So, we considered tray column, and we have seen how the tray column looks like, its different types of tray, and under which we have seen there are three different types of tray generally used. One is bubble cap, then sieve tray, and then valve tray. So, valve tray is a proprietary trays which are used for tray column, but bubble cap and sieve tray they have detailed informations are available in the literature for their design. And then we have seen what are the different conditions happens or occurs in a tray column when we change the gas and liquid flow, and how the flooding, entrainment that occurs. So, we have also discussed about the tray spacing, and weeping, flooding, entrainment. So, and we have seen how to take care of these parameters. In this lecture, module 3, lecture 3, we will continue our tray column design. So, we will see how to design a tray column. So, tray column design we will consider in under this lecture. While designing a process plant or a part of it, complete material and energy balance calculation for every piece of equipments are required, and this can be established for the design only when we have certain parameters in our hand. One of them is the flow rate is known to us. Then we need to know the composition of the mixture, both for the liquid phase composition and the gas phase composition, the temperature and pressure of each stream, both the gas and the liquid stream. Each stream we should know the temperature and pressure condition, the amount of heat input, output and generation if any, because of any chemical reactions or so. So, these parameters should be available to do the detailed materials and energy balance for a particular process plants. For example, if we take a tray or a pack tower, we need to know the flow rates, the compositions, the temperature of all liquids and the gas or the vapor streams entering and leaving the tower, and then the operating pressure. So, these are required. The physical properties of the stream are also required, such as density, viscosity, diffusivity, surface tension, etc. These are required to be known or estimated for use in design calculations. So, the physical properties either has to be available in the literature or has to be estimated, which will be used in the design calculation. So, if it is a unknown solvent, unknown gas and unknown liquid mixture, these properties has to be measured or estimated using certain empirical correlations. The most common type of trays are bubble cap tray, sieve tray, and valve tray. So, these we have already introduced in the last class. So, under this trays we give a brief outline of the procedure of design of sieve tray which is called the perforated tray. Valve tray, as we said, it is a proprietary trays and only limited information on their design is available in the open literature. And as far as the design is concerned, we will outline on the sieve tray, because the design parameters for the proprietary trays like valve trays are not much available in the open literature. So far the design of sieve tray is concerned, the major items to be determined are the tray diameter. So, we need to know what would be the tray diameter, or that is the column diameter, column internal diameter. So, that has to be determined. The tray gas pressure drop. So, how much pressure drop because of the flow of the gas through the from one trace to the other through the liquid. The size and layout of the holes, hole layout and size. The tray spacing and tower internals such as downcomers and wear, and tray efficiency. All this we will discuss briefly in this lecture, but mostly the detailed design of the plate columns or the sieve tray are available in your design course, or you will learn in future. So, we will just briefly highlight to give the basic understanding on the sieve tray design. Tray or column diameter. The required diameter of a tray of column for a given flow rates of the gas and the liquid phase is determined from the flooding conditions. We know that the gas velocity in a column is gradually increased. So, if we increase the gas velocity in a column, there is a limiting velocity above which entrainment is high enough to cause accumulation of the liquid on the trays leading to flooding. After a certain velocity, or we call the limiting velocity, so under such circumstances the column will flood. The velocity corresponding to the theoretical maximum capacity of the column, that limiting velocity will correspond to the theoretical maximum capacity of the column. There are few methods of calculation of the flooding velocity. Schroeder-Brown equation gives the flooding velocity for spray entrainment flooding, and which is given as follows: VFL would be equal to CSB rho L minus rho G divided by rho G to the power half, where VL is the superficial velocity at flooding and CSB is the Schroeder-Brown flooding constant, sometimes called capacity factor, and rho L and rho G they are the density of the liquid and the gas. Although CSB is called the capacity factor and the Schroeder-Brown flooding constant, but actually this quantity CSB is not a constant. The value of empirical constant CSB depends on different parameters like tray spacing, liquid load, fractional hole area on a tray, and the hole diameter. So, these are the 4 parameters which will influence the empirical constant values of CSB of the Schroeder-Brown constant. CSB can be estimated using the following relationship: CSB equal to FST into FF into FHA into CF, where FST is the surface tension factor and which is defined by sigma by 20 to the power 0.2. Sigma is the surface tension. So, which is in unit of dynes per centimeter, and then FF is the foaming factor and it is usually 1 for non-foaming systems. For many absorber it may be 0.75 or even less, and FHA is 1 for AH by AA greater than equal to 1.0, and it would be equal to 5 into AH by AA plus 0.5 where for AH by AA less than 0.1. This AH by AA is the ratio of vapor hole area to tray active area. So, AA is the tray active area and AH is the vapor hole area. So, vapor hole area divided by tray active area, this ratio is related with the FHA, another factor, hole to tray area, and which is used over here to calculate CSB. Now, CF, which can be related with alpha log 1 by m plus beta. This alpha can be related with 0.0744 T plus 0.01173 with this equation, and then beta is also a constant, can be related with 0.0304 into T plus 0.015. So, with these two relations alpha and beta are related, and then we can have m is the flow parameter, which also depends on liquid and gas flow and their density. So, L is the flow rate of the liquid, G is the gas flow rate, and then rho is the density of the gas, rho G, and rho L is the density of the liquid. So, L by G into rho G by rho L to the power 0.5. T is the trace spacing over here in equation of alpha and beta, trace spacing which is in meter, and the value of m over here is in the range of 0.01 to 0.1, then use m is equal to 0.1 in the above equation. So, we can use as 0.1 at the extreme case. Typically, the column diameter is based on a specific fractional approach to flooding. So, fractional approach to flooding means fractional flooding is F, and then we can write dt column diameter would be equal to 4 Qg divided by F into VFL 1 minus AD by AT into pi to the power half. So, it is suggested that AD by AT must be chosen based on the values of m, as AD by AT would be 0.1 when m is less than 0.1. AD by AT would be 0.1 plus m minus 0.1 divided by 9 for this range when m is greater than equal to 0.1 and it is less than equal to 1, and it would be 0.2 for m greater than 1.0. So, we can use these values over here and VFL, and given a particular flooding conditions with a volumetric flow rate, we can calculate the tower diameter, okay, or column diameter. Now, in most sieve trays, the holes are placed in the corner of equilateral triangle at a distance between centers from 0.25 dH to 0.5 hole dia. So, this pitch length from here to here would be 2.5 dH to 5 dH, that is a hole dia. So, it would be in these cases in most of the sieve trays. For this arrangement, we can write AH by AA would be equal to pi by 4 sin 60 dH by pH whole square, which is equal to 0.907 dH by pH square. So, AH is the vapor hole area and AA is the tray active area. Now, we need to know the downcomer geometry. LWR is the weir length, which is given over here. This is the weir length, and AD is the downcomer area here, AT is the tower cross sectional area AT, and DT is the diameter of the tower, which is equal to twice RO here. RWR is the distance of the weir from the center of the tower. So, we can calculate AD by AT would be equal to theta minus sin theta by 2 pi. So, here LWR by dt would be equal to sin theta by 2, and RWR by dt we can write half into cos theta by 2. If the tower diameter calculated from the equation is less than 60 centimeter, then a packed column is generally used. As per the equation given for the calculation of the tower diameter, tray spacing must be specified. On the other hand, the tray spacing is also depend on the tower diameter. So, these are the recommended values for the tower diameter, and you can see over here the tower diameter which is in meter is 1 or less, when the tray spacing you can set as 0.5 meter, and when it is between 1 to 3, the tower diameter between 1 to 3, the tray spacing is 0.6 meter, and between 3 to 4 meter tower diameter, the tray spacing is 0.75 meter, and 4 to 8 meter the tray spacing is 0.9 meter. So, these are the recommended values for the tower diameter which need to be used for the design. Therefore, the calculation of tower diameter is an iterative procedures. So, we have to use the iterative procedures, and an initial value of Ts, that is tray spacing, is chosen when Ts is 0.6 m at the lower values, and then gradually we can iterate with the higher values of tray spacing. The tower diameter dt is calculated based on the values of tray spacing. The values of Ts is modified based on the recommended values and estimate the dt again. This above procedure is repeated until the convergence is achieved. Now, there is a pressure drop in the tray. So, pressure drop of a sieve tray we can calculate tray pressure drop, fractional loss for vapor flow through the short tube formed owing to the plate thickness, and an exit loss. So, this short tube means when we make a hole with a particular thickness of the tray, there will be a short tube like arrangement. So, owing to that, when the vapor flows through that, you consider a vapor flowing through a short tube due to the thickness of the plate, plus an exit loss, plus pressure drop due to the liquid hold up on the tray, and plus the pressure drop due to surface tension. So, all this has to be accounted for. Dry tray pressure drop, then we have to consider pressure drop due to liquid hold up and pressure drop due to surface tension. Under dry tray pressure drop, we have two types, due to the frictional loss, which is due to the forming the tube, short tube due to the plate thickness, another one is an exit loss. So, this has to be considered under the dry tray pressure drop. So, we can write the equation H T is equal to H D plus H L plus H S, where H T is the total pressure drop per plate of centimeter of liquid, it is in centimeter of liquid, and H D is the dry plate pressure drop centimeter of liquid, and H L is the hydraulic head of, that is centimeter of liquid. So, and H S is the head loss due to the surface tension, that is centimeter of liquid. So, total would be the dry plate pressure drop, hydraulic head and the head loss due to the surface tension. These three pressure drop are added to get the total pressure drop in a ship tray. Now, given as modified orifice type equation, Ludwig in 1979, this is the equation HD would be equal to 0.051 into Vh by C naught to square into rho g into rho w by rho L whole into 1 minus AH by AA whole square. So, with this we can calculate HD, where Vh is the gas velocity through the holes in meter per second, rho w is the density of water, C naught is the orifice coefficient and AH and A is already mentioned earlier, it is a whole area AH and AA is the active tray area. The rho g, rho w and rho L are conventionally used. Then surface tension pressure drop we can obtain from the force balance between the internal force of bubble and the surface tension force. So, from this Hs would be equal to 6 sigma L by G rho L by dH. So, using this we can calculate the surface tension force, where it is assumed that maximum bubble size may be taken as the hole diameter. So, this is the assumptions if you wanted to calculate the pressure drop due to surface tension force, and where we consider dH is the maximum bubble diameter which can be achieved. Now, at very high vapor rate, entrainment is significant, that we know. So, decreases tray performance, and the fractional entrainment EF can be defined as mass flow rate of the entrainment liquid divided by the mass flow rate of upward gas. So, it can be calculated using the correlation. EF would be equal to 0.00335 H beta by Ts to the power 1.1 rho L by rho g to the power 0.5 HL by H beta to the power k. The tray efficiency, which is defined as the fractional approach by a real tray to an equilibrium tray. So, we need to know the tray efficiency. So, in tray efficiency we will discuss few terms. One is point efficiency. You can see in this case the contact among the phases is not uniform at all locations. So, the point efficiency will vary. Yn plus 1 local is the local concentration of the gas leaving n plus 1th tray, and Yn local is the local concentration of the gas leaving at nth tray. So, these two are local concentration, and Yn star local is the concentration in equilibrium with Xn local. So, this Yn star local is in equilibrium with Xn local. So, with this nomenclature we can write the point efficiency as EOG equal to Yn local minus Yn plus 1 local divided by Yn star local minus Yn plus 1 local. Numerator is the actual entrainment of the gas divided by the maximum entrainment possible. So, this will give the point efficiency of that particular tray. Now, what are the assumptions taken over here? The local concentration Xn local is constant in the vertical direction. This means that the liquid is vertically well mixed. Thus, the concentration is uniform in the vertical direction at any point on the tray. So, this local concentration Xn is constant in the vertical direction and then uniform throughout the tray. The gas phase is in plug flow, that is the gas changes along the depth. It is a plug flow, so its concentration will change along the depth of the flow. In order to achieve high tray efficiency, mass transfer coefficient and interfacial area must be higher. Now, we will relate the point efficiency with these parameters, interfacial area and the mass transfer coefficient. Let Gs is the molar gas flow rate and assumed to remain constant. dl is the small thickness of dispersion. ds is the small area of the tray, which is shown over here. Steady state mass balance over the small thickness dl. Then we can write the rate of mass transfer of gas would be equal to gas flow rate into area into thickness. So, this is the rate of mass transfer. Gs is the molar flow rate into the differential area of the tray into the change of concentration dy. Now, assumptions: the concentration of gas Y undergo change in concentration dy in the height dl. So, it is assumed that the gas mass transfer occur from gas phase to the liquid phase, and again the rate of mass transfer we can write Kya into ds into dl and yn star local minus y. So, capital Kya is the overall gas phase mass transfer coefficient and A is the specific interfacial area, it is area per unit volume of the liquid. The rate of mass transfer as we have defined earlier. So, this is over here, and ds into dl is the small volume of dispersion. A ds dl is the gas liquid contact area in the small volume of the dispersion, and yn star local minus y is the local mass transfer driving force at any height L from the tray floors. The rate of mass transfer to the gas phase is this one, which is already mentioned, and then rate of mass transfer we can also correlate with this equation. And then if we equate equation 1 and 2, we can get Gs into ds into dy would be equal to Kya ds dl into the concentration gradient yn star local minus y. So, if we integrate over the height, then we will get integral yn plus 1 local to yn local dy by yn star local minus y would be equal to integral 0 to L Ky into A dl by Gs. So, from here we can get ln yn star local minus yn local divided by yn local minus yn plus 1 local would be equal to Ky Al by Gs. So, this is defined as NTOG, number of turns per unit of the gas phase, NTOG. So, if we just subtract both sides with minus 1, and then we can write this equation minus ln 1 minus yn local minus yn plus 1 local divided by yn star local minus yn plus 1 local would be equal to minus ln 1 minus EOG would be equal to NTOG. So, EOG we can write would be equal to 1 minus e to the power NTOG. NTOG, as we said, number of overall gas phase transfer unit, and if NTOG is very high, EOG approaches unity, that is the tray approaches ideal tray performance when NTOG approaches infinity. In order to obtain EOG, Kya is needed, Alternatively, the following correlations may be used to calculate the EOG for shift tray. So, one of them is EOG would be equal to 1 minus exponential minus 0.0029 divided by 1 plus m Cg by Cl into root over dg into 1 minus beta divided by dl into Ah by Aa whole into Ref to the power 0.4136 into HL by dH to the power 0.6074. Here Ref is the Reynolds number of the fluid, which is defined as rho g Vh into H capital L divided by mu g beta. Cg and Cl is the molar concentration of the gas and liquid. M is the local slope of equilibrium curve, and dg and dl are the diffusivity of the gas and liquid. Now, there is another efficiency is called the Murphy efficiency. To define Murphy efficiency, these are the following assumptions taken: the gas leaving the dispersion at different locations of a tray get mixed up before entering to the upper tray. So, the concentration of the liquid changes as it flows over the tray. Let Xn is the concentration of the liquid leaving of the nth tray, and Yn star is the equilibrium concentration corresponding to Xn. So, EMG is defined as Yn minus Yn plus 1 divided by Yn star minus Yn plus 1. Here Yn and Yn plus 1 is not the local concentration, it is the average concentration of the gas leaving nth and n plus 1th tray respectively. So, in case of the point efficiency, we have considered the local concentration, but in this case we have considered the average concentration in case of Murphy-Stretch efficiency. Cases will be considered depending on the degree of mixing between vapor and liquid phase. Case 1, if the liquid on the tray is completely bag mixed, the liquid concentration Xn is uniform everywhere. So, now for complete bag mixing systems, the liquid concentration Xn will be uniform throughout the tray. So, EMG would be equal to EOG. So, point efficiency would be equal to the Murphy efficiency. Now, for case 2, if the liquid flows on the tray as plug flow and no axial mixing in the liquid phase, in this case EMG would be equal to A into exponential EOG by A minus 1, where A is L by mg, it is absorption factor, m is the Henry's law constant, and L is the liquid flow rate and G is the gas flow rate. So, overall tray efficiency EO is the number of ideal trays divided by the number of real trays. If in point 1, if gas and liquid flow rates G and L and the slope of the equilibrium curve remain constants over the section of the column, EMG remains same for all trays. So, then the relation between EO and EMG is as follows: EO would be equal to ln into 1 ln 1 plus EMG into 1 by A minus 1 divided by ln 1 by A. Here if A tends to 1, then EO would be equal to approximately equal to EmG. So, when this absorption factor tends to 1, then the overall tray efficiency would be equal to the Murphree stage efficiency or tray efficiency. Now, let us consider a small problem to look after the design aspect which we have discussed for the tray column. Ammonia is absorbed by pure water from air ammonia mixture using a sieve tray tower. The mixture contains 10% ammonia and 90% air. It is desired to remove 90% ammonia. The gas enters at the bottom of the tower at a flow rate of 150 kilomole per hour at 298 Kelvin and 1 atmosphere pressure. The water is fed at the top of the tower at flow rate of 150 kilomole per hour. Assume surface tension of liquid is 72 dynes per centimeter. The diameter of the sieve tray is given 2 millimeter, which is on an equilateral triangular pitch of 10 millimeter. The density of the liquid is 1000 kg per meter cube. The recommended foaming factor is 0.8. Now, design the tower for an 75% approach to the flooding velocity. Now, let us move forward to solve this problem step by step. So, average molecular weight we can calculate for the gas mixtures which are given. We have 10% ammonia, 90% air. So, 0.1 into 17 the molecular weight of ammonia plus 0.9 into 29. So, it is 27.8. Now, G dash gas flow rate which is given 150 kilomole per hour. So, we can calculate in terms of kg per second. G dash would be 150 into average molecular weight 27.8 divided by 3600 seconds. So, it would be 1.158 kg per second. Now, rho g would be equal to Pt mg average divided by RT. So, it is 101.3 total pressure into the average molecular weight divided by R into T. So, which is coming around to be 1.137 kg per meter cube. Now, ammonia absorbed. So, we have a gas flow rate of 150 kilomole per hour. So, 10% of that is 150 into 0.1 and out of that 90% has to be absorbed. So, into 0.9 into the molecular weight of the ammonia. So, would be 229.5 kg per hour. So, L dash is also over here is 150 kilomole per hour for water which is fed at the top. So, it would be 150 into 18 plus 229.5 divided by 3600. So, the water flow rate would be L dash would be 0.814 kg per second. The density rho L is 1000 kg per meter cube at 298 Kelvin. M would be equal to L dash by G dash into rho g by rho L to the power half. So, if we just substitute the values of L dash then G dash into rho g 1.137 which we have calculated and then the density of liquid which is given 1000 kg per meter cube to the power half. So, we will get is around 0.024. AN by AH would be equal to 0.97 dN by Pn whole square which is equal to 0.97 2 by 10 whole square. So, which is coming out to be 0.037. Now, assume trace spacing Ts is 0.6 meter. Then we can calculate alpha would be equal to 0.0744 into 0.6 plus 0.0 0.1173 would be equal to 0.0564. So, alpha we can calculate, then we can calculate beta using the relations which are provided in the lecture. So, which will be around 0.0332. Since m is less than 0.1, use m is equal to 0.1 as we have said earlier. So, Cf would be equal to alpha log 1 by m plus beta. So, beta and alpha we have calculated, m we can use 0.1. So, Cf we can calculate is about 0.0896. Now, since An by At is less than 0.1, we can use the relation of FHA, which is 5 into An by Aa plus 0.5, which is equal to 5 into 0.037 plus 0.5, which is equal to 0.618. So, FHA we can calculate, and then FST would be equal to sigma L divided by 20 to the power 0.2. So, sigma L which is given over here is taken as 80 dynes per second. So, 80 divided by 20 to the power 0.2, which is equal to 1.92. FF is the factor, flooding factor FF, which is equal to 0.8, which is given, and CSB we can calculate using this relation. So, all the parameters FST, FF, FHA and CF are known. So, we can calculate the values of CSB, which is 0.0572 meter per second. Now, Qg would be equal to G dash by rho g. Rho g we have calculated, rho g are given, then G dash we have calculated. So, Qg would be equal to 1.019 meter cube per second. So, volumetric flow rate of the gas we can calculate. VFL we can calculate using this relation, which is 0.0572 into rho L minus rho g divided by rho g to the power half, which is 1.696 meter per second. So, VL FL we can calculate. Since m less than 0.1 m, we can take AD by AT is equal to 0.1. For 75% approach of flooding, we can calculate dt, which is equal to 4 Qg divided by F VFL into 1 minus AD by AT into pi to the power half. So, if we just substitute the values, then we can see 4 into 1.019 divided by 0.75 into 1.696 into 1 minus 0.1 into pi to the power half. So, then we will get know the values of dt is around 1.064 meter. Now, since the calculated values of diameter is between 1 and 3, so it is in between 1 and 3 meter, and we assume Ts is equal to 0.6 meter, which is recommended trace spacing. So, no further iteration is needed. So, that is within the acceptable limit. So, this way we can do the tower design for the plate towers, and with this discussion we will complete our tray tower design discussion, and thank you for hearing this lecture, and we will continue our design of the towers for packed column in the next lecture.